So hello everyone, thanks for coming. So I'm going to talk about a story about zero-cost abstraction and what happens when they fail and they actually code something at runtime and what can we do about it. So just a bit on myself as introduction. So I'm a product manager at a French company named Quarkslab. I'm working on an LLVM-based obfuscating compiler and a whitebox cryptographic library. On my free time, I also work on some open source projects. So one of them is named Dragon FFI, which basically allows to call C function from Python seamlessly, so you don't have anything to describe. You can just include header, it basically works. And another project which is named Python, which is a subset of Python converter, which converts subset of Python to C++. It aims at having performance. I also enjoy doing cryptography and reverse engineering and various things. And so why I'm talking about my life here is that because what I'm going to present is a bit of mix of all this stuff. And so yeah, the story is a story of a compiler bug which affects the performances of Python generated code. So it's not a bug in terms of like it breaks the semantic of the code. It's a bug which affects the performance of the generated code. So I will use that as an excuse to introduce the LLVM IR, intermediate representation, to try to show how such a bug can be understood and potentially fixed. And basically what I hope in the end of these 30 minutes that you will be more comfortable to dig into a compiler, that you will try and see this not as a black box, but maybe as a kind of gray box, and maybe a white box for some people. I see some LLVM experts in the room, so I think they're already in the white box side of the thing. Anyway, and so yeah, after all, your compiler is just another C++ project. It's a kind of complex one. But yeah, if you know C++, you can read these things. All right, so as any modern storage, it's made to sell commercials. So I will have some commercial break in this presentation to show some concepts I will use during the talk. So the first one is about vector instructions. So it's used the model that we call SCMD, which is named single instruction multiple data. So the idea is to say we have instructions in our CPUs which can take multiple data and do multiple operations at once. So here, for instance, I have a vector of 4 32-bit integers. I have 2 of them. I use this instruction which is named an x86 P8D, and we basically return the vector of 4 32 integers and by performing 4 additions. So if this instruction has the same number of cycles as a classical serial instruction, I will basically go 4 times faster. So that's the theory. All right, so let's go back to the bug. So it all starts with Python, and the Serge Gueton, which is the main mentor of this project, asked me and said, okay, Adrien, can you take a look at the code that is generated and see if there are performance issues? I say, okay, so I take a simple thing, which is this code, which basically takes 2 vector 32-bit integers, add these 2 vectors and generate a new one. So it's a really simple operation. So I try to benchmark this. All right, so again, it's a classical C for loop, which is a simple one. So I take this code, so it takes 2 buffers of 32-bit integers, a size, and an array to return the results, and perform the addition. All right, it's a simple code and simple loop. So here's just another advertisement. I use Dragon FFI to code this from Python. All right, and then so I do a first benchmark, like how much time does it take to sum 200,000 of this number? So it's like 45 microseconds. And then I do the same with Python. So here with this Jupyter notebook, I have a Python magic that will do the compilation and other things for this function. And then I can just benchmark it. And then I have 110 microseconds. So it's like twice slower. So what I would expect, because in the end, I would expect the same performances as the C code, because we convert Python to C++. And so if everything goes fine, I should be close to that. All right, so there's something going wrong here. So where is the problem? So if we think about it, the main thing that can go wrong is vectorization doesn't happen. It's this SCMD thing I showed at the beginning. The compiler didn't manage to do it, and so it's slower. So can we try to confirm this thing? So if we use Clang, we have this flag which says, okay, tell me if you can vectorize the loop or not. So if I use this with my C code, which is very simple, it says, okay, I vectorize this loop. So I know that Clang do the right thing, so that's fine. And if I do the same on the code generated by Python. So just to see that the code that Python generates, so you actually don't want to read that. And so if I ask Clang if you vectorize something, it actually tells me I just have a warning here, but I don't have the same remark I had before. So somehow vectorization didn't work. All right, so another way to show that is to look at the generated LLVM code. So I won't do that here because one at a time, but if you comfortable with that, it's another way to see it. All right, so how do we fix it? So there are many solutions. First one is to write instruction-based code or ASM code by hand. It's a tedious work because you have to support every architecture. It's not portable. If you have AVX 512 that goes out, you need to rewrite everything, so you don't want to do that. You can also use a high-level C++ library that exists. So there are two of them that I know of. The first one is named Both SCMD, which is done by Joël Falcou, which is here if you want to talk to him about it. The other one is XSCMD by Quarkslab, which is another French company. And actually, Python already does this. So that's fine, my bug is fixed. I actually only have to build my code with the XSCMD or Boost SCMD, that's fine. So we can tell, okay, Adrien, why did you come from Paris to tell us that? So the question is, maybe we could try to fix this for everyone else. So maybe we can try to actually fix the compiler so that we manage to vectorize this code. And we will, in the end, we'll have the same performance as my simple C loop. All right. So what I could do is say, okay, I took this very huge, horrible Python-generated code, send it to the LLVM guys and say, okay, people, this doesn't vectorize. And I'm pretty sure that I won't have any answer because they don't want to read that code. They don't have the time to say, okay, we'll read the root cause and all these things. So what we try to see here is how we can do that and maybe generate and send them an easier report, an easier bug fix to work with. All right. So second commercial break, I'm going to talk about the LLVM IR intervention representation. So this is a classical compilation flow. So you have Clang, which is a front end in the LLVM sense of the thing. It will take C or C++, generate this intervention representation, do a lot of optimization in here, and actually vectorization happens at this stage, and then generate code based on the backend you want. Actually, the backend, you also have optimization at this point, but we won't talk about it because, anyway, we can't do anything. So some definitions. So the LLVM IR, we can see that as a kind of structural and type assembly. So it's structural, so we have a module, which is basically the compilation unit with global variables, it's functions. Functions are made of basic blocks, and basic blocks are made of instructions. It's usually called the static singular assignment form. So it's basically a word to say when you have a register which is assigned to a value, it can change, it's immutable, and that's it. And the nice thing about this IR is that it can be serialized and deserialized into a textual form that a human can actually read. And I think it's one of the reasons it had so much success in the past. Some remarks, so it's still a low-level virtual machine, so the CIBI is partially resolved. So for instance, if you have a structure with only a scalar within it, maybe the structure won't exist in the end, or stuff like that. When you generate the IR, it's already generated for the target machine you have, so you can take, you can't easily take the IR, for instance, for Linux x64 and run that on Windows x32. It won't work out of the box. All right, so let's see what it looks like. So here I've got a simple addition of two 16-bit integers. If I ask Clang to emit this IR, so it's basically only the two flags to put, it will generate this. So we have multiple things here which are interesting. We get this triple, which basically is the combination of the OS and the CPU architecture you are building for. We have the data layer here with many information. So we stuff, for instance, like what is the size of a pointer. And then we get the actual code, and here it says, all right, I've got A and B, which are the parameters of my functions, and then I add these two parameters that are returned. So that's pretty straightforward, all right? So here you can see we use the optimization level 1, so this IR is already optimized. If we take a look at the IR which Clang actually generates, without any optimization thing, we have more instructions. And then we see, okay, how can we optimize that? So we have this nice tool which is named opt in LLVM, which you can use to apply optimization by hand on this IR and see the actual results. So here the first optimization we maybe can see is say, okay, we've got this allocate instruction, which is basically how we allocate a 16-bit integer on the stack. We have a virtual stack and we can allocate stuff on it. I've got the same here, and then we just store and load a value in this memory slot. So we could remove this memory slot. It's no use in the end. So we have an optimization pattern that does that, which is literally named memory to register, and which will remove this allocate, store, and load chain of instruction and replace this directly by A or by B. All right, and then we still have 4 instructions there. So we've got this 0 extend instruction, this addition, and this trunc. So why do we have that? In C, when you do A plus B on 16-bit integers, we get this integer promotion rule. And so we'll do actually the addition of the int type in the end. And so that's what's actually happening here, all right? But we could make something better. We can just do add of 2 60-bit integers, so that one pass I can do that is int combine. And int combine will try, which is a really useful optimization in the end, and try chains of instruction and say, okay, I know something which is shorter and which is more efficient, and I will use that in the end. So that's what it does here. It say, okay, I can repeat the 4 instructions, but only the addition in the end. All right. So now more complex IR. So like I said, we have basic blocks and instructions. And so you actually have the CFD of the instruction directly within the IR. So here I've got a loop, which is a pretty simple one. It will return computation, which is done here. And so for instance, here it just compare the number of iterations with 0. If it's true, it will go within the loop body. And if it's false, it just return. And here maybe you can notice these three instructions we have here and here. And so what are these three instructions for? Like I said, we use the SSA form. So we can't modify the value of a register. And so for instance, for the return value, we say, okay, if you come from the entry block, you actually got the value 1 because we don't do any computation. That's the original value here. And if you come for the loop for body, but where you use the actual computation you've done, all right? And that's what's done here within the loop body. And that's the only thing to understand here. All right, so another concept I will use is induction variables. So if you take the Wikipedia definition, it's actually pretty straightforward and simple. It's a variable that will change, increment or decrement each loop iteration or any linear function of other induction variables. So here in this example, I is 1 and J is 1 because it's I by 7. All right. So now we know all of this. We need to make this minimal reproducer to work to find out where the bug is. So the first thing we have is that Python uses expression templates. So if you had the talk before, you know what it was by Joel. If not, if we can try to explain this in one simple phrase, it's basically a set of techniques to statically represent expression at compile time and then evaluate them with actual expression. So it's generally used to achieve handmade loop fusion. So for instance, in our case, we have A plus B, and we want to take their expression and evaluate them on every element of our arrays. So that's the obsession Python uses, and Python expects the compiler to remove somehow this expression, and so that it should not cost anything in the end. All right. If we use Clang, it can also tell us why it did not manage to vectorize. So that's why to see here. So sorry, it's not here. Here. All right. So if I ask Clang to say, okay, tell me why you did not manage to vectorize my loop. And if I know a bit how Python works, then you say, okay, this loop hasn't been vectorized. And I've got an error message here. And this is basically in Python's line that evaluates an expression template. So it already says, in this loop, I didn't manage to vectorize because of this problem. Okay. So now we can, with some instant, we can manage to make a reduced test case. So in this one, we have what we call an add zip operator, which is basically an iterator, which is basically a structure with 2 pointers, and when we dereference this iterator, it just do the addition. All the other stuff here is a boilerplate code just to make a random access iterator. And then how do we make our actual function here? We just create these two add zip operator, and then we use stud copy, and it should generate the loop with the addition and all this stuff. If we take a look at the generated assembly here, we see there is no vectorized instruction. We only have this add here and this loop. So the vectorization actually failed. So we managed to recreate a simple example with the same bug. All right. So now that we have that, we need to try to understand what's going on within the compiler, why it didn't manage to vectorize this. So one way to do it is to try to make small visual diff of the IR optimized for the simple C code, which is here. All right. and the one which is generated when we use our complex iterator. So that's the LLVM IR which is generated for the simple C code, and this one is the one generated for this add-zip iterator. The thing that we can see that we've got this bunch of int to pointer and pointer to int instructions, so it does what you think it does. Int to pointer, we take an integer, translate that to a pointer type, and pointer to int, we do the reverse operation. All right. So we can keep this in mind. If we have the talk, if we ask Clang, like I showed, it will show us the same message. So we can also take this message and say, all right, I actually don't really understand what it means, but I try to use a really disparate tool to understand what it does, which is named grep. So I will grab this message error within the LLVM source code. I will end up in this code, which is part of the vectorizer code, sorry. And here I've got the message which says, all right, there's a phi node, well, there's a value that shouldn't be notified as rejection outside the loops. That's what our message was. And then we've got this debug thing that say, I found an unidentified phi node, and that's a phi node, which is actually a problem. The thing we have here that's within this debug macro thing, and if you have a Clang in release mode, which generally you don't have any way to have this because it's not included in the release binary. So what you can do is that you can actually compile Clang in debug mode. It's really not hard to do. It uses a nice CMake system to do that. You just need this line of CMake and a Ninja or Make or whatever you want. And you compile that. It takes a bit of time. So for instance, 20 minutes on my machine. But it's actually really easy to do. So you do that, and then you use Clang and say, OK, show me this debug information for the loop vectorized path. And so at some point, you say, it will dump here the unidentified phi that it found. So we can see in the LLVM IR which one it is. So if we take a look at it, it's actually the phi node which is linked to these two int pointer and pointer to int instructions. And it says, all right, I can't manage to see this phi node as an induction variable. And if you think about it, the vectorizer needs to understand every variable which is in the loop and to be able to say, this is induction variable, so I know how to vectorize this. If there's an instance of a variable that it doesn't understand, then it just say, I don't know what to do, it doesn't do anything. All right. So to answer this question, are this variable induction variable, it uses another analysis which is called scalar evolution. So in one sentence, it's something that computes the change in the value of scalar variables over iteration of the loop. So for instance, for the counter, I just say, well, I is equal to 0 plus the index of the loop. So there's actually a nice talk about this in LLVM 220, 19. If you're interested, it's actually nice math behind it. If we take a look at the source code of this analysis, it says, all right, if I've got this int to pointer to int stuff, I don't do anything with it because I can have some aliasing problem, and we won't talk about it, but basically, it confirms that's the problem we have. So what can we do now? If we want to really confirm that it works, if we remove this round trip of conversion, we can write an out of tree LLVM pass that will try to fix that. So in LLVM, you have this system where you can register transformations in various steps of the pipeline. And so here I can say, register my pass before vectorization. So before the vectorization tries to happen, I will remove this round trip and see if it works. All right. So that's what we do here. Here the original LLVM IR with this pointer to int into pointer round trip. And here, this is the cleaned LLVM IR, so it has been removed and everything is as we want it to be. So if I ask Clang to actually vectorize this code, it actually happened, and I will see, for instance, here I have this addition on a vector. That's what I want. Okay. So what do we do from here? We actually can't remove this into pointer to int round trip because we break some semantics, so it's not really valid to do this. So we need to understand what actually creates this instruction and maybe try to fix that. So if we take a look at the variable name we can have within Clang, it say this thing is named SA or A here. All right. So if you know a bit about it, you know it can be linked to scalar replacement of aggregates, which is another optimization. It's actually also a really important one when we do this kind of stuff, because that's the optimizations that try to split a structure of scalars and to actually transform that into actual scalars where we can do classical optimization. Here, my structure of scalars are my iterator with these 2 pointers, and at some point, we transform the structure within 2 simple pointer it can reason on. And so that's the path that actually generates this. And so maybe the proper fix would be to fix S error A. Okay. So now that we got all of this, we can make an actual bug report. So you've got the LLVM bug tracker. If you want to register on that, you can also have the LLVM dev mailing list, where you can actually ask questions and have sometimes answers, usually answers. Here are the links and the discussion we had for this particular bug. So what was the actual fix that happened? Because this thing has been fixed in Clang 6. It's actually been fixed indirectly because of the change in this ins combined path we talked about in the beginning. With the transformation that say, alright, so that gets a final with the pointer with the int pointer. At some point, it's actually a final on a pointer, and so we change that. So here, if we take a look at the IR before ins combined and after ins combined, we see that here we've got this final, which was the problem, which has an integer type, and here it has been changed with the final with the pointer type. We don't have any int pointer or pointer to int conversion, so the vectorizer is happy and everything goes fine. So the actual fix was not here done where we thought it would be, but I mean, it works. All right. So a bit of conclusion of this. So did we fix the actual Python code in the end? So if we try to run the Python code generated with Clang 8 or maybe Clang 9, which will, I think, be released soon, or maybe it's already released, it still fails at it. So we fixed our test case, but we didn't fix the whole problem because if we take the Python code, we still have non-vectorized code that are still an issue. So we need to redo this again. All right. So I hope maybe I'll have time to do this at some point. Okay, so what I hope we learn in this talk. So we can see that compilers are a way to debug their analysis. When you have a problem, if you actually know how to do it, if you read, there's a lot of documentation about it, you can have some hints why the optimization will expect didn't work, or why it works if it works, all right? And actually, it's interesting to report this because if compilers fail at simple things like that, I mean, there's an issue. We can't use zero-cost abstraction and expect everything to work. So a bit of discussion about that. Usually in C++, we like to say, okay, C++ is fine because you can make abstraction. It's going to be optimized away. It's really cool. We can add layers and layers and it don't cost anything. But actually, if we look at the standard, there are a few things that are guaranteed, but not a lot of them. So it basically works because we have good optimizing compilers. There's some static code that says, don't worry, the compiler works. But when it doesn't work, well, you're on your own. So the issue is for something like Python, when the performance is actually a contract with your user. When someone uses Python, he expects better performances than the original Python code, for instance. Well, you've got no way to guarantee that in the end. You just say, well, it should work. I think it works. But if you don't use a good compiler or stuff like that, maybe you don't have the performance you would expect. So what can you do about that? So that's some ideas. I don't say that's good ideas. I say that's some concepts we can think about. So the first one would be to say, okay, I have optimization that I want to guarantee. Maybe I could use pragmas. Maybe some pragma that say, okay, if you can vectorize that loop, actually emits an error because for me, it's an error if this loop is unvectorized. And we can help to trigger or to find out optimization problems at compile time and not at runtime. Can we also try to have some level of optimization guaranteed by the C++ standard? It's actually really complex because you will need to say, if you use the optimized guaranteed level 1, it means that you have this path and this path and this path run. But do we really want to do that? I don't know. Okay, so some other practical ideas we can have. So there's a nice tool which is named FileCheck, which is kind of grep, an enhanced grep, if you want to say that. So we can, for instance, say, okay, we check my assembly, or if I, for instance, add this PAD in my assembly in the test, but it is platform dependent. The other thing I can say is maybe try to check that on the LLVM IR. It's still platform dependent, but it's a bit more high level. And that's something I will just demonstrate here. So it's a simple thing. So first thing I do is I run Clang 4 on my code with the iterator. You can see all right. And then use file check, and file check will actually parse this, which say, okay, you find the function which is named up. So here it's a regular expression because the symbol is mangled, so it's not that perfect, but just to get the idea. And then you need to find out if you have a vectorized instruction after this label. All right. So, sorry. So here I'd say, okay, I didn't find any vector expression, so it's actually an error. And if I can put that in my test suite, I can only figure out directly if I have problems. All right, and now for the demo, if I use the actual path to clean the IR that I've done, if I use file check over there, then it works because it actually been vectorized, so everything is fine. So that's really handmade here, but the idea is to say, maybe we can make more production-ready tools to check on the kind of stuff. And that would be all for me. I put some takeaway here if you want, maybe try these things by yourself. Like you said, Serge Guelton, we did the author of the Python project. For the actual Python project, a discussion about this talk. And if you have any question, we have 3 minutes and 40 seconds.